Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my fifth lecture on the concept of time response of control system. In my previous lectures, that is in the first lecture, I discussed what is time response, that is steady state as well as transient state responses, discussed various test inputs. We have also derived the expression for steady state error and what are the various factors on which steady state error depends and their effects. In my second lecture, I discussed various tutorials based on various error coefficients, that is Kp, Kv and Ka, and their corresponding steady state errors for step, ramp and parabolic inputs. In my third lecture, we have derived the time response of first order system with unit step, unit ramp and unit parabolic inputs. We also derived time response of second order system with unit step input for underdamped, undamped, overdamped and critically damped cases. And in my fourth lecture, I also derived the various time domain specifications, that is rise time, peak overshoot, settling time, and also discussed their corresponding definitions. So in today's lecture, let us see some of the tutorials based on second order system. The first tutorial, the unity feedback system, is characterized by the transfer function g of s is equal to k by s into s plus 10. Determine k such that the system has damping ratio of 0.5 for this value of k. Also determine settling time, peak overshoot and peak time for unit step input. So we are given the open loop transfer function. So since it is unity feedback system, h of s is equal to 1. So by default we always consider negative feedback system. So the expression for closed loop transfer function is g of s by 1 plus g of s into h of s. Since h of s is 1, so c of s by r of s will be equal to g of s by 1 plus g of s. So g of s is already given, that is k by s into s plus 10. So substituting that will give me my closed loop transfer function c of s by r of s to be k by s square plus 10s plus k. So comparing this with my second order standard equation, that is omega n square by s square plus 2 zeta omega ns plus omega n square. So here if I compare, I can see omega n square is equal to k and 2 zeta omega n is equal to 10. So from that I will get the expression for omega n, because since I already know the value of zeta in the question itself, he has already mentioned that zeta value is 0.5. So from this, if zeta value is 0.5, that will give me the value of omega n to be 10 radians per second. If omega n is 10 radians per second, so from this expression k value will be 100. So the first part we have already determined, that is determining the value of k. The second part, we need to find the expression or the value of settling time, peak overshoot and peak time. We already discussed the expressions for all these time domain specifications. So settling time, assuming it is 2%, ts is 4 by zeta omega n. So zeta value is given as 0.5, omega n we have obtained as 10. That will give me the value of settling time as 0.8 seconds. Next, peak overshoot as well as peak time. Peak time, we know the formula Tp is equal to pi by omega d, where omega d is omega n into root over 1 minus zeta square. Zeta is 0.5, omega n is 10. That will lead my peak time TP to be 0.363 seconds. And lastly, peak overshoot, you know the formula, it is e power minus pi zeta by root over 1 minus zeta square into 100. Zeta is 0.5, and if I substitute in the formula, that will give me the percentage MP to be 16.3%. Moving forward to second tutorial, for the given system, determine damping ratio, natural frequency and expression for output response if subjected to unit step input. So G of S is given. It is 20 by S plus 1 into S plus 4, and H value is unity. It is very obvious from this question. So considering the negative feedback, we know the expression for closed loop transfer function G of S by 1 plus G of S into H of S. In this case, H of S value is 1. So substituting the value 20 by S square plus 5S plus 4 plus 1 plus G of S. That will lead me to the expression of C of S by R of S as 20 by S square plus 5S plus 24. One thing here clearly we can see that the obtained expression is not in the standard form. So in the numerator value and the last term of the denominator value must be same for it to be in the standard form. So since in this case the obtained transfer function is not in the standard form, we'll only compare the denominator polynomial, that is S square plus 5S plus 24 with S square plus 2 zeta omega n S plus omega n square, which will give me the value of omega n to be 4.89 radians per second, and correspondingly from this expression zeta value can also be obtained, which is 0.51. So the first part is completed, that is we have found damping ratio, we have found the natural frequency omega n. So now we need to find the expression for output response. So first let us write that expression which I obtained in standard form. So I have taken 20 common in the numerator and I have multiplied and divided by 24. So that will bring my expression to the standard second order form. Okay, so we know the expression. We have already derived this expression in previous lectures, that in second order control system the expression for output response is 1 minus e power minus zeta omega n t by root over 1 minus zeta square into sine omega dt plus theta. So now we need to find the values of theta, omega d, omega n and zeta. We need to know these values. So zeta we already found out, omega n also we have found out, and omega d is nothing but omega n into root over 1 as zeta square. That will give me the value as 4.21 radians per second. Okay, so theta is nothing but tan inverse of root over 1 minus zeta square by zeta. Remember the answer that you get when you do it in calculator, you will get the value in degrees. You need to convert that into radians. Okay, so on converting into radians, I get the answer as 1.03 radians. So substituting all the values in the expression above, that will give me the output response as C of t is equal to 20 by 24 into 1 minus 1.16 e power minus 2.5 t sine 4.21 t plus 1.03. Moving forward to third tutorial. So given that the percentage peak overshoot is 25%, peak time is 4 seconds. It is asking you to find the values of K1 and K2, assuming it is unit step input. So first I need to find the expression for overall transfer function. So we already know the block diagram reduction technique. So using that, considering it is negative feedback, so g of s will be nothing but k1 by s square, and h of s will be 1 plus k2 into s. Okay, so since the formula is g of s by 1 plus g of s into h of s, that will give me the expression of the closed loop transfer function as k1 by s square plus k1 k2s plus k1. So comparing this with my standard form, that will give me the relation between k1, k2 and zeta. So omega n is root over k1 and zeta will be 1 by 2 root k1 into k2. Okay. So now using these two data that is given, that is Tp is equal to 4 seconds and Mp is equal to 25%, we need to first calculate the value of zeta and omega n. So from Mp we will get the value of zeta, from Tp we can get the value of omega n. So peak overshoot formula is e power minus pi zeta by root over 1 minus zeta square into 100. That is given as 25%. So that will lead my e power pi zeta by root over 1 minus zeta square as 0.25. So since I need only this expression, natural logarithms, when I apply on both sides, that will give me minus pi zeta by root over 1 minus zeta square as log 0.25, which will give me as minus 1.38. So cross multiplying and squaring on both sides, that will give me the value of zeta as 0.40. Now peak time is also given. Peak time expression, we know it is pi by omega d, that is pi by omega n into root over 1 minus zeta square. So since we already know the value of zeta, which we have obtained in previous case, that will lead me the value of omega n as 0.85 radians per second. You can do the calculation on your own. So next, now since we have obtained the values of zeta and omega n, we need to find what is the value of k1 and k2. So substituting the values that we have got, that will give me the value of k1 as 0.73 and the value of k2 as 0.94. Yes, next tutorial, the system is described by the differential equation d square y by dt square plus 4 dy by dt plus 8y is equal to 8x, where x is the input and y is the output. Determine all time domain specifications for unit step input. So applying Laplace on both sides, which will give me s square into y of s plus 4s into y of s plus 8 into y of s is equal to 8 into x of s. So from that, if I take y of s as common, that will give me y of s into s square plus 4s plus 8 is equal to 8 into x of s. That will give me my transfer function y of s by x of s as 8 by s square plus 4s plus 8. Comparing this with my standard form and finding the values of zeta and omega n. So that will give me the value of omega n as 2.83 radians per second and zeta value as 0.70. Now we know the formula for all the time domain specification, just we need to substitute in the respective formula. So omega d is nothing but omega n into root over 1 minus zeta square. So we know the value of omega n zeta, that will give upon substitution as 2 radians per second. So percentage MP, we all know the formula, it is e power minus pi zeta by root over 1 minus zeta square into 100. So on substitution of zeta value, that will give me percentage MP as 4.33%. Next is the settling time 4 by zeta omega n. Upon substitution of zeta and omega n values will give me the value of settling time as 2 radians per second. Next, for calculating rise time, we first need to find the values of theta, which is tan inverse of root over 1 minus zeta square by zeta. That will give you the value in radians, in degrees, that you need to convert in radians. So upon conversion, that will give me the value as pi by 4 radians. So due to which the rise time, the formula is pi minus theta by omega d, which will give you the value as 1.17 seconds. And lastly, peak time is pi by omega d, and if I substitute the value of omega d, will give me the value of peak time as 1.57 seconds. So there is not asked, but anyhow, if I want to find output response also, so I can calculate, since we know the formula, C of t is 1 minus e power minus zeta omega n t by root over 1 minus zeta square into sine omega dt plus theta. So if he asks you to find the response also, then you can do this step, otherwise there is no need. So we know all the values, isn't it? Just if you substitute, that will give me C of t as 1 minus 1.41 into e power minus 2t into sine 2t plus pi by 4. So next is the unity feedback control system. Has an amplifier of gain Ka10 and gain ratio G of S as 1 by S into S plus 2. In feed forward path, a derivative feedback H of S is equal to S into K naught is introduced in the smaller minor loop around G of S. He has asked us to find the derivative feedback constant K naught such that the damping factor is 0.6. So first, using block diagram reduction technique, we will find the transfer function. Okay, so eliminating feedback, we know the in place of this we can write as G of S into 1 plus G of S into H of S, and these two are in cascade. G of S is already given, so H of S is also given. So doing the cascade and finding the open loop transfer function will give me the value as 1 by S square plus 2 plus K naught into S. So replacing that, and since these two are in cascade, that will give me the open loop transfer function as 10 by S square plus 2 plus K naught into S. Here H of S value is 1, unity feedback. So using that formula, if I calculate, that will give me my transfer function as 10 by S square plus 2 plus K naught into S plus 10. Comparing this with the standard form, so if I compare, then omega n square is 10 and 2 zeta omega n is 2 plus K naught. So that will give me the value of omega n as 10. Omega n square is 10. From that, omega n value is 3.16 radians per second. And the second term, that is 2 zeta omega n, is nothing but 2 plus K naught, isn't it? So that is what is written here. We know the value of zeta. We also know the value of omega n. So upon substitution, that will give me the value of K naught as 1.792. So next tutorial, we need to find the constant KT, zeta, that is damping ratio value is given, and also we need to find the values of TP, MP, omega D and TS. Okay. So we already know the formula, isn't it? So First, using block diagram reduction technique, I can first find the expression for overall transfer function. Okay, so here when I consider only this loop, okay, so eliminating feedback, that is g by 1 plus g into h. So this is g and this is h. That will give me this transfer function, that is 14 by s into s plus 14 kt plus 1.6. So again that is the expression for my open loop transfer function. Here h of s value is 1, isn't it? So it is g by 1 plus g into h. So that will give me the expression as 14 by s square plus s into 14 kt plus 1.6 plus 14. Comparing this with my standard form, omega n square is nothing but 14, isn't it? That will give me the value of omega n as 3.74 radians per second. And 2 zeta omega n value is 14 kt plus 1.6. Okay, so you can see here. So zeta is already given, that is 0.5. So from this I obtain the expression for zeta, that is 14 kt plus 1.6 by 2 omega n. This value is equal to 0.5. Omega n value also I know, that is root 14. So upon substitution, that will lead me the value of kt as 0.15. So the first part we have found out the constant kt. The second part, we know the formula omega d is omega n into root over 1 minus zeta square. That will give me the value as 3.24 radians per second. Peak time Tp is pi by omega d, and if I substitute, that will give me the value of Tp as 0.96 seconds. Next, percentage MP, e power minus pi zeta by root over 1 minus zeta square into 100. Just substituting the value of zeta will give me the percentage as 16.3%. And settling time 4 by zeta omega n. Upon substitution, that will lead me the value to 2.13 seconds. So the next tutorial, given that for negative feedback, g of s is k by s into s plus 6 and h of s is equal to 1. Determine the value of k such that damping ratio is 0.8, and for this value of k we need to find all the time domain specifications. So first let us find the overall transfer function, that is g of s by 1 plus g of s into h of s. That will lead my overall transfer function to be k by s square plus 6s plus k. And comparing this with my standard form, my omega n square will be k and 2 zeta omega n will be 6. So from that, omega n is root k, zeta is 3 by root k. But my zeta value is already known. In the sum he has already mentioned that the damping ratio is 0.8. So upon substitution of the value of zeta will give me the value of k, which is 14.06. So since k is also known, just by squaring the value will give me the value of omega n. Okay, so by taking the square root of k value will give me the value of omega n, which is 3.75 radians per second. Since omega n is known, we know the formula omega d is omega n into root over 1 minus zeta square. So just upon substitution of values of zeta and omega n, it will give me the value of omega d as 2.25 radians per second. So the first part is completed. Next we need to find the time domain specifications. So peak time is pi by omega d. Just by substituting the value will give me the value of peak time as 1.39 seconds. settling time is 4 by zeta omega n. That upon substitution will give me 1.33 seconds. Next, percentage peak overshoot, which is e power minus zeta pi zeta by root over 1 minus zeta square into 100. Just substituting zeta as 0.8 and taking natural logarithms, and if we do all that procedure, that will give me the percentage as 1.51%. And delay time is 1 plus 0.7 zeta by omega n. So we know the value of zeta and omega n. Just by substitution will give me the value of delay time as 0.416 seconds. Rise time, it is pi minus theta by omega d. We know theta value is tan inverse of root over 1 minus zeta squared by zeta. That will give me the value of theta in degrees. So we have to convert that into radians, and just by substituting in the formula will give me the value of rise time as 1.11 seconds. So the last tutorial for today's lecture, the unity feedback control system is open loop transfer function is given as g of s is k by s into st plus 1. By what factor gain must be reduced so that peak overshoot of unit step response is reduced from 75% to 25%. Okay, first let us consider the overall transfer function. Since h of s value is 1, upon calculating the overall transfer function will give me k by t by s square plus 1 by t into s plus k by t. Comparing this with my standard form of second order system will give me the value of omega n square as k by t to zeta omega n as 1 by t. So upon simplification, omega n is nothing but root over k by t, and 2 zeta omega n is nothing but 1 by t. So here I have two cases. One is 75% peak overshoot, 25% peak overshoot. So firstly, let us, for 75% peak overshoot, let us assume damping ratio is zeta and gain value is k. We know the formula of peak overshoot, that is e power minus pi zeta by root over 1 minus zeta square. Since it is 75%, 0.75, taking natural logarithms on both sides will give me the damping ratio in first case as 0.09. In second case, for 25% peak overshoot, I assume damping ratio as zeta 1 and gain as k1. Here also, upon the substitution of the formula, e power minus pi zeta 1 by root over 1 minus zeta square is 25%, so it is 0.25. Taking natural logarithms on both sides will give me the damping ratio in this case as 0.41. So we can conclude that in order to change the peak overshoot from 75% to 25%, zeta, that is damping ratio, must change from 0.04 to 0.40. That is what we have concluded from this analysis. Okay. So next, we already know that omega n is root over k by t and 2 zeta omega n is nothing but 1 by t. So from that, zeta in terms of k and t I can express as 1 by 2 into root over kt. Okay, so let us take both the cases. In first case, since zeta is zeta, and second case it is zeta 1, so I am comparing both the expressions. So in first case as well as second case, and taking the ratio of these two. So if I take the ratio of these two expressions, that will give me zeta by zeta 1. So zeta we have obtained as 0.09, zeta 1 as 0.40. Taking the ratio, which will give me the ratio, or I can say in other words, the relation between constant k and k1, as k1 is equal to 0.05 k. So in this case, what is our main aim is to find what factor, by what factor gain must be reduced. Okay, so from this I can conclude that gain must be multiplied by 0.05 in order to change my peak overshoot from 75% to 25%. This concludes my today's lecture on the tutorials of second order system control system. In my next lecture, we'll continue solving some more tutorials based on second order control system. Thank you.